Hello everyone, I am Dr. VRAO. In the last video, that is lecture 31, we had gone through the equilibrium constant and applying law of mass action to reversible reaction and units of Kp, Kc and relation between Kp and Kc and Kp and Kx. Now, we shall go through the factors influencing the equilibrium constant, right? Factors influencing the equilibrium constant. Factors influencing the equilibrium constant. Let us see the factors which influences the equilibrium constant one by one. The first one is stoichiometric representation of equilibrium constant. Stoichiometric representation. Stoichiometric representation. Stoichiometric representation influences the equilibrium constant. For example, if you take a reversible reaction A2 plus B2 gives rise to 2AB. Right. So, if we write the equilibrium constant K, that is, we can write the equilibrium constant as a concentration of products to ratio of equilibrium constant is ratio of concentration of products to concentration of reactants. So, concentration of AB square by concentration of A2 into concentration of B2, and it is called Kc because these concentrations are molar concentrations. This is Kc. Okay. For example, if we revert to this reaction, that is, I wrote this reaction A2 plus B2 gives rise to 2AB. So, stoichiometric representation is like this. Right, if I revert this reaction, that is 2AB gives rise to A2 plus B2, then we can write equilibrium constant Kc dash, because we are reverting the reaction, that is why I use a dash for the equilibrium constant. Kc dash is equal to concentration of A2 by concentration of B2 by concentration of AB square. So, if you observe these two equilibrium constants, there is difference between these two equilibrium constants. That difference is due to stoichiometric representation of the reversible reaction. And one more thing is that Kc is equal to Kc or Kc dash is equal to 1 by Kc. 1 by Kc. For example, if you revert this reaction, that is, if you write this 1 by Kc, then this goes to, that is, 1 by concentration of AB square by concentration of A2 into concentration of B2. How this fraction becomes? This fraction becomes this denominator goes to numerator, that is concentration of A2 by concentration of B2 by concentration of AB square. So, it is Kc dash. So, we can write Kc dash is equal to 1 by Kc or Kc is equal to 1 by Kc dash. That is the one factor, and the second one is if we divide this equation with a factor 2, that is, for example, the equilibrium constant Kc is, what is that Kc? Concentration of AB square by concentration of A2 into concentration of B2. So, this is the equilibrium constant, but if you divide this whole equation with a factor 2, that is 1 by 2 A2 plus 1 by 2 B2, when we divide, the 2 cancel, that becomes AB. So, the equilibrium constant is Kc dash is equal to concentration of AB by concentration of A2 power 1 by 2 and concentration of B2 power 1 by 2. Okay, and this is the equation, and we can develop a relation between Kc and Kc dash when we multiplied with a factor 2 or n, right. So, Kc is equal to Kc dash equal to Kc power 1 by 2, because when we apply a root on this for Kc, then 1 by 2 this 2 are cancelled, and concentration of A2 power 1 by 2 and concentration of B2 power 1 by 2, then that is equal to Kc dash. So, Kc dash is equal to Kc power 1 by 2, that is when we divide a reaction with a factor n, then the new equilibrium constant will be root of nth root of the previous value, Here the equilibrium constant is Kc for the initial reaction, equilibrium constant is Kc, and when we divide this equation with the factor 2, that equilibrium constant is Kc dash, and Kc dash is equal to Kc power 1 by 2, that is, when we divide a reaction with a factor n, then the new equilibrium constant will be nth root of the previous value, equilibrium constant, right. So, this is one factor. I repeat, when we divide a reaction with a factor n, then the new equilibrium constant will be nth root of the previous value. Next reaction is next example, 1 by 2. Let us see what happens when we multiply the equation with a factor n. 1 by 2 A2 plus 3 by 2 B2 gives rise to AB3. Okay, AB3. So, this is the reaction. So, if we the equilibrium constant for this reaction is Kc is equal to concentration of AB3 by concentration of A2 power 1 by 2 and concentration of B2 power 3 by 2. Okay. And when we multiply this equation with factor 2, that is when we multiply the equation with 2, this is 2 and this is 2 and this 2 get cancelled, this 2 and this is 2, this 2 cancel, that is A2 gives rise to A2 plus 3B2 gives rise to 2AB3. That is the new equilibrium constant Kc dash is equal to concentration of AB3 power 2 and concentration of A2 into concentration of B2 cube. Okay. 3. Okay. And when we multiplied the equation with a factor 2, then the new equilibrium constant Kc dash is equal to when we multiply, that is when we multiply this equation with 2 factor 2, for example, if you multiply this equation this equilibrium constant with 2, that is the AB3 square, and when we multiply when we applying square, this 2 cancel and this 2 cancel, that becomes Kc dash. So, Kc dash is equal to Kc power n. So, when we multiplied the equation with a factor n, the new equilibrium constant will be nth root of the multiplied by nth power of the previous value, Okay. So, you should what you should keep in your mind is that when we divide an equation with a factor n, then the new equilibrium constant will be nth root of the previous equilibrium constant. And if we multiply the equation with the factor n, then the new equilibrium constant will be nth power of the previous equilibrium constant. Okay. Kc dash is equal to Kc power 1 Kc power n. When division is when it is division, that is Kc dash is equal to Kc power 1 by n, right. So, these are the factors which influencing the equilibrium constant. Okay. This is the one factor, this is one of the factors influencing the equilibrium constant. And the most important factor that influences the equilibrium constant is temperature. So, next one is temperature. Temperature is the one and only experimental factor that influences the equilibrium constant. I repeat, temperature is the only one and only experimental factor that influences the equilibrium constant, and the influence or effect of temperature on equilibrium constant is given by a equation, given by a relation, that is log K2 by K1 is equal to delta H by 2.303 R into 1 by T1 minus 1 by T2. Okay. This is the equation and if you want to how this equation comes actually to explain the all this reaction, how this reaction come, that needs a long derivation. That is why I shall take a direct relation of equilibrium constant with the temperature. Okay. So, log K2 by K1 is equal to delta H by 2.303 R 1 by T1 minus 1 by T2. Okay. To prove this equation, to get to know how this equation comes, we need to perform a long derivation. That is not needed. What you should remember is log K2 by K1 is equal to delta H by 2.303 R 1 by T1 minus 1 by T2. So, this is enough. This equation is enough to know the effect of temperature on equilibrium constant, right? Okay. So, log K2 by K1, where K1 is the equilibrium constant at temperature T1. Okay, and K2 is the equilibrium constant. K2 is the equilibrium constant at temperature T2. Okay. So, there are three important cases is there. Okay. First case is case 1 is if delta H is equal to 0, if delta H is equal to 0, change in enthalpy. I shall explain the thermodynamic terms when I deal with the thermodynamics chapter. Okay. Here that is a different chapter. That is why I could not explain the what is meant by enthalpy. Okay. So, I definitely will discuss the thermodynamic terms when we discuss the thermodynamics chapter, right. If delta H is equal to 0, what happens? This all becomes 0. So, then log K2 by K1 is equal to 0. That is that implies K2 by K1 is equal to 10 power 0. So, n power 0 is equal to 1. So, K2 by K1 is equal to 1. So, therefore, K2 equal to K1. K2 equal to K1. That means that temperature has no effect on equilibrium constant. That means temperature is the equilibrium constant is independent of temperature when delta H is equal to 0. This should be keep in your mind. When delta H is equal to 0, equilibrium constant is independent of temperature. Okay. So, that is the case 1. And case 2 is when delta H is equal to positive, that is when delta H is positive, log K2 by K1 is positive, that is greater than 1. That means K2 is greater than K1. That means that delta H positive, that means forward reaction is endothermic. If delta H is equal to positive, that indicates forward reaction is endothermic reaction. If forward reaction is endothermic reaction, then with increasing the temperature, equilibrium constant increases, right. I repeat, if forward reaction is endothermic reaction, then with increasing the temperature, equilibrium constant value also increases, right. Next, case 3 is case 3, delta H is equal to negative. That is, forward reaction is exothermic. When delta H is negative, forward reaction is exothermic reaction. Forward reaction is exothermic reaction. That means log K2 by K1 is less than 1. Okay, that is K2 is less than K1. Okay, right. This means that delta H is, whenever delta H is negative, that means that forward reaction is exothermic. That is, with increasing the temperature, equilibrium constant decreases. Equilibrium constant decreases, right? Okay, so there are 3 points here. When delta H is equal to 0, when delta H is equal to 0, that means the equilibrium constant is independent of temperature. If delta H is positive, that means forward reaction is endothermic reaction, and with increasing the temperature, equilibrium constant also increases, right? And if delta H is negative, that means the forward reaction is exothermic reaction. With increasing the temperature, equilibrium constant value decreases, right? So this is the effect of temperature on equilibrium constant, right? Okay. Okay, so factors influencing equilibrium constant are stoichiometric representation of a reaction, and temperature has a greater effect on equilibrium constant, right? So another concept, that is equilibrium constant and free energy, the relation between equilibrium constant and free energy. Equilibrium constant and free energy. Right. So to explain the relation between equilibrium constant and free energy, we need a basic thermodynamic equation. That is, we need to know the thermodynamic basic thermodynamic equation. That is, so delta G is equal to delta G naught plus RT ln Q. Okay, delta G is equal to delta G naught plus RT ln Q. Q is the reaction quotient. Okay, this is the fundamental thermodynamic. This is the fundamental equation in thermodynamics. When we deal with when I deal with thermodynamics, definitely I will explain the how this equation comes, right? Next, so reversible reactions, the most common phenomena in the reversible reactions is equilibrium. There exists equilibrium is established in reversible reactions, and we need to we can write the equilibrium constant only for reversible reactions. So we can write we can write this we can apply this thermodynamic equation to equilibrium constant. Okay, so what happens when equilibrium is established in a reversible reaction? Delta G, the free energy of this system, that is at equilibrium, delta G, that is change in free energy, is equal to 0, because at equilibrium the concentration of products and concentration of reactants remains constant. Okay, concentration, okay, density, some physical properties, density remains constant. Okay, So, at equilibrium the concentration of products is equal to concentration of reactants. We know that because in reversible reactions tug of war has been takes place and the rate of forward reaction is equal to rate of backward reaction. What does it mean? It means that the concentration of products is equal to concentration of reactants. Whenever the concentrations are equal, there is no free energy change. Okay, it is the important point. Whenever there is no change in the concentration, then there is no change in Gibbs free energy. So, at equilibrium concentration of products equal to concentration of reactants. So, delta G change in Gibbs free energy is also 0. So, when delta G is equal to 0 and delta G equal to 0, it is the condition, such that condition at equilibrium, and at equilibrium Q equal to K, reaction quotient Q is equal to K. So, this equation becomes this delta G is equal to 0 and this equation becomes delta G naught is equal to minus RT ln K, minus RT ln K, and we can write this minus delta G RT is equal to ln K, and we can write this K equal to e power minus delta G naught by RT. Okay, the relation between equilibrium constant and free energy is K is equal to e power minus delta G naught by RT. So, what is that relation? K is equal to e power minus delta G naught by RT. Okay, here the two conditions is there, two conditions are there. One, if delta G naught is less than 0, that is if delta G naught is equal to, if delta G naught is less than 0, that is if delta G naught is less than 0, then what happens? Delta G naught is less than 0, that means that is a negative value, that is a negative value. So, this delta G naught is less than 0, that means that delta G naught is negative value, then e power minus delta G naught by RT is positive. E power minus delta G naught by RT is positive. E power minus delta G naught by RT is positive. That is e power minus delta G naught by RT is greater than 1. That is K greater than 1. That is K greater than 1, because K is equal to e power minus delta G naught by RT and e power minus delta G naught by RT is greater than 1. Okay, that is positive means greater than 1 and K greater than 1. Okay, K greater than 1. So, K greater than 1, that means that the reaction is spontaneous. Reaction is spontaneous reaction. That forward reaction is a spontaneous reaction. Whenever K greater than 1 and delta G naught is negative, delta G naught is negative, then that indicates, that implies that the forward reaction is spontaneous reaction. Forward reaction is spontaneous reaction. Okay, usually we say that when delta G is negative, that reaction is a spontaneous reaction. And one more thing is that we are discussing the relation between equilibrium constant and Gibbs free energy. Whenever standard Gibbs free energy is negative, then K greater than 1, that means forward reaction is a spontaneous reaction, right? And the another case is second case, when delta G naught when delta G naught is greater than 1, when delta G naught is greater than 0, when delta G naught is greater than 0, sorry, and delta G naught is greater than 0, that means that delta G naught greater than 0, that is positive, that is e power minus delta G naught by RT is negative, that is e power minus delta G naught by RT negative, that is less than 1, that is e power minus delta G naught by RT is less than 1, that means that k less than 1, k less than 1. So, when delta G naught is positive, and k less than 1, that means that forward reaction is non-spontaneous reaction. Okay. So, delta G naught is positive and k less than 1, forward reaction is non-spontaneous, and when delta G naught is negative and k greater than 1, that means that forward reaction is spontaneous reaction. So, by the values of equilibrium constant and by the values of delta G, we can define the we can say that whether the forward reaction is spontaneous or non-spontaneous. Okay. So, these are the relations between equilibrium constant and free energy. I hope you all understand this lecture, and in the next video I shall come up with a new concept. Thank you.